Today we're explaining attention mechanisms, the mathematical black magic that makes transformers work and your GPU bills explode. Not the hand-wavy models pay attention to important words bullshit, but the actual linear algebra nightmare where query, key, and value matrices somehow learn to think. 3 engineers, 1 math professor who's seen too much matrix multiplication, and 45 minutes of pure mathematical suffering. I'm Sam, and someone's definitely crying over softmax by the end.
I've implemented attention from scratch 6 times, and I still don't understand why it works. The first time, I spent 3 weeks debugging because my attention weights were all zeros. Turns out I was initializing my weight matrices wrong, and the model was literally paying attention to nothing. Like a teenager, but with gradients.
My specialty is vision transformers, and attention mechanisms are why I have trust issues. You feed it an image, it splits it into patches, does some matrix magic, and suddenly it knows where the cat is. I can implement it, I can optimize it, but explaining why dot product attention works, that's where I start questioning my PhD.
I teach linear algebra to graduate students. When attention mechanisms became popular, suddenly everyone wanted to understand matrix multiplication again. The math is actually beautiful. It's just scaled dot product attention. But somehow this simple operation learned to understand language, recognize objects, and generate art. Mathematics doesn't explain why, only how.
Ethan, you're our mathematical guide through this linear algebra hellscape. Rachel and Kevin, prepare to explain why matrix multiplication became consciousness. No hand-waving about learned representations.
Let's start with the basics. What is attention at the mathematical level?
It's a way for each position in a sequence to look at every other position and decide how much to care about each one. Like, each word can attend to every other word in the sentence.
That's the intuition. What's the actual computation?
Attention equals softmax of query times key transpose divided by square root of dimension times values. Attention Q KV, softmax QKT slash square DKV. It's just matrix multiplication with extra steps.
Good, now explain what Q, K, and the fifth actually are. Where do they come from?
They're all linear projections of the input embeddings. You take your input X and multiply by learned weight matrices WQ, WK, and WV. So Q equals XWQ, K equals XWK, V XWV, same input, 3 different perspectives.
Why 3 matrices? Why not just one?
Because it works. Honestly, I don't have a principled answer. Query represents what am I looking for, key represents what do I have to offer, value represents what information should I contribute, but why this specific decomposition works is still black magic to me.
Let's dive into the computation. What happens when you multiply Q and K transpose?
You get an attention score matrix. Each position I can attend to position J, so QKT gives you an n times n matrix where entry I, J represents how much position I should attend to position. Higher scores mean stronger attention.
What's the dimensionality here? If your sequence length is n and embedding dimension is d.
Q is n times d, K is n times d, so KT is d times n. QKT is n times n. For a 1,000 token sequence, that's a million attention scores. For GPT-4's 32K context, that's over a billion attention scores per head. That's why long sequences murder your GPU.
Explain the scaling factor. Why divide by square root of?
Without scaling, the dot products get huge as dimension increases. If equals 512, dot products could be hundreds or thousands. When you feed massive numbers to softmax, it saturates, everything becomes 0 or 1, no gradients flow, training dies.
Why specifically square root of? Why not just?
If Q and K have independent elements with unit variance, their dot product has variance proportional to dk. Square root scaling makes the variance unit again. It's about keeping the distribution well-behaved for softmax. Pure statistics, not magic.
Now softmax, what's it actually doing to your attention scores?
Converting raw scores to probabilities. Each row sums to 1, all values between 0 and 1. Position I's attention distribution over all positions. But softmax is brutally competitive. It amplifies differences exponentially.
What does brutally competitive mean mathematically?
Softmax of, the largest input gets exponentially more probability mass. Small attention score differences become huge probability differences. Winner takes most dynamics.
Finally, what happens when you multiply by the fifth?
You get the weighted combination of value vectors. If position I attends strongly to position J, it incorporates a lot of position J's value vector into its output. The attention weights determine how much of each position's information to mix in.
So the output at position I is a weighted average of all value vectors.
Exactly, output I equals sum over J of attention weightage Vj. It's just a fancy weighted average. But somehow this simple operation learned to do syntactic parsing, coreference resolution, and factual reasoning. I have no idea why.
Now the complexity explosion, multi-head attention. Why not just one attention head?
Because one attention pattern isn't enough. You need different heads looking for different types of relationships, syntactic dependencies, semantic similarities, long-range connections. Like having multiple specialists instead of one generalist.
How many heads do modern models use? What's the computational cost?
GPT-3 has 96 attention heads per layer, 96 layers. That's 16 different attention patterns running in parallel. Each head computes its own Q, K, V matrices and attention weights. The compute scales linearly with number of heads.
What's the memory complexity for attention?
The attention matrix is ON2. For sequence length n, you need N2 memory just to store attention weights. GPT-4's 32K context needs over 1 billion attention scores per head. With 96 heads per layer and 96 layers, that's astronomical memory requirements.
Why is this quadratic scaling a problem?
Double the sequence length, quadruple the memory and compute. Going from 2K to 32K context means 256x more attention computation. Your GPU cluster becomes a small nuclear reactor, and your electricity bill funds a small country.
Let's talk about what attention actually learns. Can you interpret attention patterns?
Sometimes, some heads learn to attend to previous tokens, some to specific syntactic roles, some to semantic relationships. But many attention patterns are completely uninterpretable. We can see what the model attends to, but not why.
What about the claim that attention heads learn linguistic structures?
Some do, some don't. You'll find heads that track subject-verb agreement, others that follow coreference chains. But you'll also find heads that seem to do nothing interpretable yet are crucial for model performance. It's not a clean mapping to human linguistic concepts.
The fundamental question, why does attention work so well?
Nobody knows. Theoretically, it's just a content-based routing mechanism. But somehow this simple matrix operation learned to perform complex reasoning, understand context, and generate coherent text. The math is simple, the emergent behavior is inexplicable.
It's the biggest mystery in deep learning. We can implement attention, optimize it, scale it to billions of parameters. But we don't understand why this particular architectural choice unlocked such powerful capabilities. We're riding a mathematical wave we don't comprehend.
Jesus Christ, so we've built intelligence using weighted averages. Nobody knows why it works, and the compute requirements grow quadratically with anything useful. This is fine.
Welcome to modern AI. We've accidentally discovered that matrix multiplication can think, and now we're building civilization on top of mathematical operations we don't understand.
This episode was brought to you by Engineer Panic, where simple math meets incomprehensible emergence, because understanding why attention works is less important than accepting that it does. We're back, let's talk about the practical nightmare of implementing attention mechanisms. Rachel, what's the most frustrating part?
Memory management and numerical stability. Attention matrices are huge and softmax is temperamental. One wrong initialization and your gradients explode or vanish. I've spent weeks debugging attention implementations that looked mathematically correct but numerically unstable.
The masking is hell. Causal attention, padding masks, key masks. Get any of it wrong and your model either cheats by seeing future tokens or crashes during training. Attention masking bugs are the most subtle and destructive.
And the optimization challenges. Flash attention, sparse attention, linear attention, everyone's trying to solve the quadratic scaling problem, but each solution has different trade-offs and failure modes.
What about alternatives to attention? Are we stuck with this quadratic nightmare forever?
There are attempts, Mamba, RWKV, linear attention variants. They solve the scaling problem but often sacrifice some capability. It's like attention found this perfect sweet spot that's computationally expensive but behaviorally optimal.
In Vision, we're seeing hybrid approaches, attention for global context, convolutions for local patterns. But pure attention transformers still dominate on many tasks. The quadratic cost seems to buy you something irreplaceable.
From a mathematical perspective, attention is solving an assignment problem, which positions should interact with which others. The quadratic complexity might be fundamental to this type of reasoning.
What keeps you up at night about attention mechanisms?
That we're building increasingly powerful systems on mathematical foundations we don't understand. Attention works, but we don't know why. What happens when we scale it further? What emergent behaviors are we not prepared for?
The interpretability crisis. We can visualize attention patterns, but we can't explain why specific patterns emerge or predict what new patterns will appear at larger scales. We're flying blind with very powerful systems.
That attention might be a local optimum, not a global one. We've invested so much in this architecture that we might be missing better solutions. Mathematical monoculture is dangerous.
Any advice for engineers trying to work with attention mechanisms?
Understand the math deeply but don't expect to understand the emergence. Implement it from scratch at least once. Debug attention patterns visually, and always question whether you really need the full quadratic complexity.
Master the implementation details, proper masking, numerical stability, memory optimization. The math is simple, but the engineering is brutal. And always profile your attention computation, it's usually your bottleneck.
Learn the linear algebra, but also study the alternatives. Attention isn't the end of the story, it's just our current best solution to the interaction modeling problem. Stay curious about what comes next.
This has been absolutely mind-melting. We've learned that attention is just fancy weighted averages. Nobody understands why it works so well, and the compute requirements are bankrupting small countries. Sweet dreams.
Thanks for the mathematical crisis, Ethan. Now I'm going back to implementing flash attention and pretending I understand why matrix multiplication learned to think.
And I need to explain to my manager why our vision transformer needs 40 gigabytes of VRAM just to process a single high-resolution image. Quadratic scaling is a cruel mistress.
Keep implementing, keep questioning, keep marveling at the mystery. Attention mechanisms are the closest thing we have to magic in mathematics. Embrace the incomprehensible beauty.
This has been Engineer Panic, where elegant mathematics meets existential confusion. Until next time, remember, attention is all you need, understanding is optional.